We are going to start with chapter 10, and we're starting with 10.2. So let's go ahead and talk about these radical expressions. So first of all, a radical expression is something that has a square root. All right. Now take a look at this one. Here we have the square root of 20. This symbol we know is, right? That's what makes it a square root. But the stuff inside 20 is the radicand. We call that the radicand. So the blue is, the symbol is the radical. So this is called a radical. And anything that goes inside is a radicand. Okay. So let's talk about the perfect squares for a minute. We've done this before when we were doing the perfect squares trinomials, right? So the perfect squares, right? 1 squared is 1, and then 2 squared is 4, and the next one up is 9. What's the next one? 16, and then 25. What's next? 36. What's next? Okay, so that's 7 squared. What's 8 squared? 64, 81, 100. Look at you, 121. What else? 144. Good. What's the next one? It's 196. So this one I always remember because the 6 and the 9 just get flip-flopped. And then 225. That's awesome. So that goes from 1 to 15. Okay. So, all right. So that's how we do this. So now, a square root, if I have the square root of a number, right? If I have perfect squares, basically, I'm looking for what number times itself gives me a 25. And because this, if I have square root of 25, what's 25? It's 5 times 5, right? So the square root of 25 is 5. Okay? Now, the square root of 0, we're just going to remember this, it's 0. We're just going to remember it. Okay. The square root of 36, right? That's 6. Again, if you know your perfect squares, which you should, at this point, nobody should be thinking about what is a perfect square and what is not. It should be very, very automatic. Just like how Ethan was doing it earlier, that's how I need all of you guys to be able to do it. I'll get your question in a minute. Okay? So we know 121 is a perfect square. So there are two things here. First, you need to know the perfect squares that we listed so that when you see a perfect square, 196, 225, 121, first you need to recognize that it's a perfect square, right? So if you're walking around and somebody says 81, you need to recognize that that's a perfect square. Next, you need to recognize what is it the square of. So 121 is the square of 11. Root 49, how much is it? 7. Okay, root 1 is 1. Okay, so I need you to memorize this one and this one. Just memorize it. We just need to know. Okay, now, the square root of 289, yeah, that's 17. Okay? Now, it's okay if you don't know that one by heart. However, this one, the square root of 400, so I think to myself, what times what is 400? And you know what? 20 times 20 is 400, so that's 20. Okay? Now, what if you don't remember, but you need to do it by hand somehow? Well, dividing, being able to divide helps. So let's talk about the divisibility rules. This is something that we used to teach when students were in elementary school, but I don't think they do it anymore. But divisibility means, is it possible to divide? The divisibility rules is, How do you know if you can divide a number by 2? How do you know? Is 27 divisible by 3? How do you know? So for example, 14. Can you divide 14 by 2 evenly?
Yes.
So 14 is divisible by 2. Can we divide 14 by 3 evenly?
No.
No. So 14 is not divisible by 3. So, but there are rules. How do we know if a number is divisible by 2? Well, it has to be an even number. So for example, 26. All right? How do you know if something is divisible by 5? It has to end in 0 or a 5. So for example, 115. I see 115, it ends in 5. I know I can divide it by 5. So let's see how we can do that. 5 goes into 11 2 times. Multiply, subtract, I get 1 and I bring down the 5. 5 goes into 15 3 times. Subtract, I get 0 remainder. Okay? All right, but I wouldn't try to divide 115 by 2 because I know it's not divisible. Okay. How do we know if something is divisible by 10? Well, it has to end in 0. Okay? So 1730, 2,450, right? 32 million. All of these can be divisible by 10. Okay. Now, how do we know if something is divisible by 3? Well, the digits have to add to a number divisible by 3. For example, 123. So look at this. I do 1 plus 2 plus 3. I get 6. Is 6 divisible by 3? Yes, then so is 123. Okay, so let's try that. Let's divide 123 by 3. 3 goes into 12 4 times. So that's 0. And then the 3 comes down. 3 goes into 3 once. There we go. Okay? Okay. Okay, any other questions? Okay. So now, what about 9? It's the same as 3. If the digits add up to a number divisible by 9, then it's divisible by 9. So for example, look at this one. 1 plus 4 plus 5 plus 8. So this is 5 plus 5, 10, plus 8, 18. 18 is divisible by 9, so 1,458 is divisible by 9. All right? And then lastly, how do we know if something is divisible by 4? The number ends in 2 digits divided by 4. So for example, look at this one, 1,324. I only look at the last 2 digits. Is 24 divisible by 4? So the whole thing is divisible by 4. Okay. Okay, you need to read this more carefully because 16 has only 2 digits and they are divisible by 4. This is divisible by 4 because the last 2 divide by 4. No, so that's why I said you got to read more carefully. Okay, so now we're going to use this to do, can you put your foot down, sit properly? Okay. We're going to do a factor tree to find the prime factorization of each number. The idea is prime factorization. What are the prime numbers? 1, 3, 5, 7, 11, right? Not 9, 13, things that can only be divided by themselves. Okay, so prime factorization is this. You take 150, okay, and you see what you can divide it by. So for example, if I wanted to do, right, if I wanted to do this one, the 123, right? Would I attempt to divide that by 2? No. How about by 3? Yes, by 3, because we just said it's divisible by 3. Okay? So take a look at this one, 150. Would you attempt to divide that by 2?
Yes.
What about 5?
Yes.
What about 10? What about 3? 3? 1 plus 5 plus 0? Yes. So the 150 can be divided by any of these. So now it's up to you, whatever you want to divide by. You know what? Since it ends with a 10, with a 0, I'm going to divide by 10. So if you divide 150 by 10, what do you get? 10 and 15. So you know how this is 10 times 15? I just write it as 10 and 15, like this. Now, is 10 a prime number? Is 15 a prime number? So we got to go more. What does 10, what do you divide 10 by? 2 and 5. Are 2 and 5 prime numbers? So I can stop. What about 15? What can I divide by? Those are prime numbers, so I stop. So now, what is the prime factorization? It's the last numbers in each branch. So do you see how we call this a factor tree? Why? Because it's like an upside down tree. This is like the root, and then these are the branches. The last leaves on each of the branches are its prime factorization. So I say 150 is equal to, and now I want to write them in increasing order. 2 times 3 times 5 times 5. Now let's do another one. 72. Yeah.
What if like the factorization? What if it was like a 10 and a 5?
Well then, but the 10 would be 5 and 2. You still do all of them that you can. Let's do a few examples and you'll see. Okay? Yeah.
So with the end, we don't know if there's 2 5s. It's basically 5 to the power of 2.
Yes. Okay, so look at this one. 72 is 9 times 8. So now, the 9 is 3 times 3. The 8 is 4 times 2. But the 4 is 2 times 2. Do you see that? I got to the 3, that was done. But so you just have to do each number until you can't go anymore. So 72 is 2 times 2 times 2 times 3 times 3. For now, I'm not going to group them. I'm just going to write them out like this. There is a reason why I'm doing this. Okay. Yes. Okay, the 124. Can I divide this by 5? What would you divide by? 4. You can divide by 4 because the 24 divides by 4. So let's see. 4, and then let's see. 4 goes into 12 3 times. 4 goes into 4 once, so 31. So it's 4 and 31. Now, the 4, I can go one more time. The 31 is a prime number. I'm done. So the 124 is 2 times 2 times 31. Okay. So now, in order to do square roots, in order to simplify square roots, we first have to do this. Okay? So simplifying square roots, right? First, you find all factors, and then you pair the common factors. For each pair, you take 1 outside the radical. Multiply the numbers you take out, And then whatever is inside, you keep them as well. All right, you multiply those as well. Okay, so let's do one. Okay, so now I have the square root of 18. So last chapter, when we were doing the roots, when we were doing like completing the square or quadratic formula, we had them and we just kept them as roots. But now we're going to learn how to simplify them. So here is what you do. You take the 18 and, okay, so 18 is 9 times 2. The first one, it could just be any factors. Then the 9 factors some more, 3 times 3. The 2 is done. So here's what I do. Square root 3 times 3 times 2, right? It was square root 18, but now 18 is 3 times 3 times 2, correct? Now, are there any pairs here? The 3's are pairs. For each pair, it comes out as a single 3. Does the 2 have a pair? No, so it stays. And so this is the answer. Okay, let's do another one.
Why is the 2 negative square root?
It didn't have a pair. Let me do a few more and I'll take more questions. So look at the 200. 200 is 20 times 10. 20 is 4 times 5. 4 is 2 times 2. Now look at the 10. The 10, I have to do it too. 2 times 5. So now, for each branch, look at the very last number on each branch. Right? Can any of them be simplified? They should all be prime. So now, this is going to equal the square root of 2 times 2 times 2, 5 times 5. Now, you have to group them in pairs. So look, one pair of 2's comes out as a single 2. One pair of 5's comes out as a single 5 and they get multiplied. This 2 has no pair, it stays. So now I have 2 times 5, 10 root 2. It's like all of these numbers are in an escape room. The only way you can escape from the escape room is if you have a partner. So the 2 2's partner up and escape. The 2 5's partner up and escape. But this 1 2 has no partner, so it stays. Okay? 2 times 5, 10, that's it. 10 root 2. Okay, let's do another one. For this one, it's getting too messy. I'm just going to go on the scratch paper here. So 72 is 9 times 8. 9 is what? And 8 is 2 and 4. And then this is 2 and 2. So look at this. This is where you have to be super careful. Because look, I have 1, 2, 3, 4, 5 numbers. So the square root of 72 is 3 2's and 2 3's. Okay? 5, 5 underneath. So what pairs up? A 2 and a 3. And you multiply them because they each come out. What stays in? A 2. So this is 6 root 2. So if they can find a pair, they come out. But the price is only one comes out, right? Like you only write it as a single 3, a single 2. Okay. Yes.
What if there's 4 or 2 pairs?
Yeah. Yes. Okay, let's do this one. Let's see if we can be a little bit more efficient for this one. So 243, I can divide this one by 3 or 9. Okay? Now, so you have to go on your scratch paper and you have to divide by 9. Right? But this is 9 times 27. Okay, so lots of work with pencil. Now, the 9, 3 times 3. The 27, 9 times 3. What else? The 9 is 3 times 3. Now, you know what? Sometimes the numbers get too big, and it doesn't make sense to rewrite all of them all over again. So what I can do is maybe I can group them from here. So look at this one. This is a group of 3s. It comes out. This is a group of 3s. It comes out. This one has no pair. It stays in. So this is 9 root 3. Right? Now, some of you don't write this. Some of you are like this. I can't even do it messy. I can't. I mean, this is clean compared to what I see sometimes. Okay? If you do this, there is no way to know what is what. So compare this to this and just appreciate how it really helps to be organized. Okay? It really helps to be organized so that you are able to keep things like in check. Okay? All right, let's do this one, the 360. Go ahead and start doing the factor tree for this one. Okay. So 360, I'm going to do 36 times 10. And then the 36 will be, what did you guys do? So you can do 6 and 6, you can do 9 and 4. It all comes out the same in the end. So this we get 2 times 3, 2 times 3, and this I get 2 times 5. Okay? And the numbers that I can pair up now are the last ones. They're the leaves on the tree, the very last leaves on the tree. So Drew, name one pair here. No, what are we pairing? So the 2s can get paired up. Okay, so that's one thing. And then these 3s can get paired up. And that's it. This 5 and this 2 stay. Huh? So the 6s are not the last thing on their list, right? It's only the very last thing. So look at what happened. The 2s paired up, the 3s paired up. This 2 didn't have a pair. This 5 didn't have a pair. They stay. So now I have some things outside and I have some things inside. So this is going to be 6 root 10. And that's my answer. Okay? No, in the end, it should all be the same. You should still get 6 root 10. Okay, let's do 48. What times what should we do? 12 times 4? Let's do that. You could also do 6 and 8. What about the 12? 3 and 4, or you can do 2 and 6. So this 4 becomes 2 and 2. This 4 becomes 2 and 2. So now look up here for a minute. When I'm pairing them up, am I allowed to take this 2? Yes. Am I allowed to take this 4? No. Okay? So here we go. So I have a pair of 2s here that come out. a pair of 2's here that come out. What stays in? A 3. So I get 4 root 3. Okay. Now, there is another way to do this, and it can be like a little bit of a shortcut. Okay? You know how root 20, okay, so suppose you have root, okay, let's do like root 48, right? We were just doing root 48. What did we say? Root 48 is 12 times 4, right? I can also write that as, because 48 is 12 times 4, I'm allowed to write it as root 12, root 4. Okay? That could be a little bit of a shortcut, but we have to be more strategic about it. So for example, root 48, it could also be root 3 times root 16, correct? Now, when I did the first one here, are any of these perfect squares? Which one? The 4. Okay. When I did this one, are any of those perfect squares? Which one? The 16. If I'm going to do it this way, I choose the option that has the biggest square root. So the 4, not that one, but the 16, yes, that one. So now, this is root 3. What's the square root of 16? 4. So this will be 4 times root 3, which is what I got before. Okay, so that's another way of doing it. But this takes a little bit more awareness of the perfect squares. Okay, so these are the perfect squares. So now let's see. 20. Can I write 20 as 2 factors and one of them is a perfect square?
Yeah.
What? 4 and 5. So root 4 and root 5. And root 4 is the biggest one. Okay? Drew, are you with me? Okay. So now, root 4 will be 2 times root 5. Okay, so that's another way to do it. All right? Okay, so now let's do the next one. 300. Let's write this as 2 squares, something times something, but a perfect square times a number. Yeah. 3 times 100. So let's do 100 times 3. Square root of 100, 10 root 3. Yes. Okay. Root 24. What do you think? What times what? So none of those are perfect squares. We need a perfect square. 6 and 4. So let's do root 4, root 6. I like to write the perfect square first so it's in proper order. Are you taking notes? So this is 2 root 6. So what about 40? What about 98? 49 times 2, right? So which one of these, right? It's the 49 times the 2. So this is 7 root 2. Okay. Okay. So now these you're going to do by the method of your choice. So here's what I'm going to do. I'm going to give you 2 minutes and I want you to do A, B, C, and D. 2 minutes. Go. So take a look at this one. 75 is what? Root 25 times root 3. 5 root 2. Now, okay, so take a look at this one. Root 42 is 2 in order. So that one is 2 times 3 times 7. There are no pairs, so it just stays root 42. That's it. It can't be simplified anymore. Yeah. No. You have to keep it as 42 because in the end, everything has to be like re-multiplied out. Okay. So 63, did we get any answers for this one? Al, did you do this one? Who raise your hand if you got an answer for this one? Matan, what did you get? 3 root 7, absolutely. Okay. So, what about this one? Did you do this one? Who did root 40? Yep, Kai. Which is 10, right? Yes. So this is root 4 times root 10, which is 2 root 10. Okay. Now the 50, this one. So here, right, let me take the 52 and I'm going to divide it by 2 and 26. And then this one is 2 and 13. Correct? So here, take a look. I already have a 3. That copies over. Times. Now for the 52. This comes out as a 2. What stays in? A 13. So finally, this will be 6 root 13. Okay? Let's do this one. Let's do it the other way. So this one is 6 times, what's root 40? Root 4 and root 10. So this one, 6 times 2 times root 10, 12 root 10. Do you see this? So this number that's outside stays with it. Okay? This number that's outside stays with it. Now here I have a negative 2 times. What do we know about the root 100? Which is what? Is 100 a perfect square?
Yes.
It's the square of what? 10. So this is negative 20. Okay, so the root 84, do you want to do a factor tree or do you want to do the squares? Let's do factor tree. I heard that first. I like the factor tree. Something about it is very soothing. So let's do 4 and 21. Let's do 2 and 2, 3 and 7. So look, this is 1/2 times, what do I take from here? 2 times root 3 times 7. So re-multiply everything. Half of 2 is what? 1 times root 21. Okay? I mean, we never write 1 times anything. It wouldn't be wrong. It's just not cool.